Everything you've ever touched, seen, or experienced exists in 3 dimensions: length, width, height. Your body moves through 3D space. Objects have volume. The universe extends in all directions. Except, none of that is actually real. In 1993, a physicist named Gerard 't Hooft proposed something so radical that it seemed like science fiction. The 3-dimensional universe we inhabit is a hologram, a projection of information encoded on a distant 2-dimensional surface. Not a metaphor, not an analogy, a literal hologram. But here's what makes this truly unsettling. Why does every attempt to combine gravity with quantum mechanics force us toward the same impossible conclusion? How can information about the inside of a region of space be perfectly encoded on its boundary? And if we're living in a projection, what's doing the projecting? This isn't fringe speculation. This is the leading framework for reconciling the 2 most successful theories in physics, theories that currently describe completely incompatible universes. The mathematics demand it, the observations support it, the implications are terrifying. By the end of this journey, you'll never see the universe the same way again. Prepare yourself. We begin. Act 1. The Discovery. The paradox that broke physics. Let's start with what seems like a simple question. What happens to information that falls into a black hole? Common sense suggests it's destroyed, lost forever beyond the event horizon. But in 1974, Stephen Hawking calculated something that shattered this intuition. Black holes aren't perfectly black. They emit radiation, now called Hawking radiation, through quantum effects at the event horizon. Over immense timescales, this radiation causes the black hole to evaporate completely. When the black hole disappears, where does the information go? Quantum mechanics has an ironclad rule: information cannot be destroyed. It can be scrambled, transformed, hidden in correlations, but never erased. This principle, unitarity, is as fundamental as the conservation of energy. But general relativity says that anything crossing the event horizon is causally disconnected from the outside universe. The information is gone. For 20 years, this contradiction paralyzed theoretical physics. Either quantum mechanics fails near black holes, or general relativity misrepresents what happens at event horizons. The entire foundation of modern physics was cracking. The radical solution. In 1993, Dutch physicist Gerard 't Hooft was analyzing the mathematics of black hole entropy, a measure of the information content of a black hole. Jacob Bekenstein had shown in the 1970s that a black hole's entropy is proportional to the surface area of its event horizon, not its volume. This was already strange. For normal objects, entropy depends on volume, how much stuff is inside. A larger box can hold more disorder. But black holes were different. 't Hooft realized this meant something profound. All the information about what fell into the black hole must somehow be encoded on the 2D event horizon surface. Think about that. A 3-dimensional object, you, a star, an entire galaxy, falls into a black hole. All the information describing that 3D object gets encoded on a 2D surface. It's like taking a full-volume book and representing it completely as writing on the book's cover, not a summary, the entire contents, perfectly preserved. This should be impossible, and yet the mathematics insisted it was true. The holographic principle emerged. Leonard Susskind, working independently at Stanford, reached the same conclusion from a different angle. He was investigating whether information truly escapes from black holes through Hawking radiation. If it does, it must be encoded in subtle correlations in the radiation, correlations that contain the full quantum state of everything that ever fell in. Susskind realized if all the information about a 3D volume can be encoded on its 2D boundary, this might not be a peculiar property of black holes. It might be a fundamental property of space-time itself. He called it the holographic principle. The principle states the maximum amount of information contained in any region of space is proportional to the area of its boundary, not its volume. Your room doesn't contain information throughout its volume. All the information is encoded on the walls, floor, and ceiling. The universe doesn't have information distributed through 3D space. All the information is encoded on a distant 2D cosmic horizon. We think we're living in 3 dimensions, moving through space, occupying volume. But we're actually patterns on a distant surface, and the 3D experience is the projection. The first evidence. This sounded insane. Physics is supposed to describe reality, not rewrite it. But then came the evidence. In 1997, Juan Maldacena, a physicist at Harvard, discovered something extraordinary while working on string theory. He was studying a particular type of spacetime called anti-de Sitter space, a negatively curved universe that curves inward like a saddle. This universe has a boundary at infinity. Maldacena showed that gravity in this 5-dimensional anti-de Sitter space is mathematically equivalent to a quantum field theory living on its 4-dimensional boundary. Not similar, not analogous, exactly equivalent. Every particle, every interaction, every quantum fluctuation in the 5D gravitational universe has a precise counterpart in the 4D boundary theory. The two descriptions are different languages describing the same reality. This is called the ADS-CFT correspondence, and it's one of the most important discoveries in theoretical physics in 50 years. It proved that holography wasn't speculation, it was mathematics. But what if this discovery wasn't the anomaly? What if it was the warning? Act 2. Accumulating evidence. Part A. Observable signatures. Evidence number 1. Black hole entropy is real. In 2002, researchers analyzing the thermal properties of black holes confirmed that Bekenstein-Hawking entropy isn't just theoretical bookkeeping. When matter falls into a black hole, the event horizon's surface area increases by an amount precisely proportional to the entropy of the infalling matter. This has been verified for rotating black holes, charged black holes, and black holes in various dimensions. The relationship holds perfectly. But here's what disturbed the physicists. If entropy measures information, and information must be conserved, then the 2D surface of the event horizon genuinely encodes the full quantum state of the 3D interior. The hologram isn't a metaphor, it's where the information actually lives. Evidence number 2. The entropy bound. In 2004, physicist Raphael Bossu formulated the covariant entropy bound, a precise mathematical statement of holographic limits. He showed that for any space-time region with a boundary surface, the maximum entropy contained in that region cannot exceed 1/4 of the boundary area measured in Planck units. This bound has been tested in countless scenarios: expanding universes, collapsing matter, cosmological horizons, quantum field configurations. In every case, the bound holds. No known physical process can violate it. systems approaching the bound undergo gravitational collapse, forming black holes before the limit is exceeded. It's as if the universe enforces a maximum information density, and that density is determined entirely by surface area. Evidence number 3, the firewall paradox. But this was only the beginning. In 2012, researchers at UC Santa Barbara discovered a new paradox that made the original information problem look simple. If information escapes from black holes through Hawking radiation, and the radiation must be quantum entangled with the black hole's interior to preserve information, then the radiation is also entangled with earlier radiation that already escaped. But quantum mechanics forbids a particle from being maximally entangled with two different systems. The only resolution, the event horizon, isn't smooth, empty space. It's a firewall, a region of such intense energy that anything crossing it is instantly incinerated at the Planck scale. This contradicted general relativity, which says crossing the horizon should be smooth and uneventful for a falling observer. The paradox became even more severe when researchers realized if holography is true, the firewall must exist, because the information cannot be in two places at once. Then, scientists noticed something worse.
Evidence number 4, quantum error correction. In 2015, physicists discovered that the mathematical structure of holography is identical to quantum error correction codes. Error correction is how quantum computers protect information from noise. You encode a single quantum bit into multiple physical qubits in a clever way so that errors can be detected and corrected without destroying the information. Researchers at Caltech and MIT showed that the holographic encoding of bulk spacetime onto boundary surfaces uses exactly the same mathematical structure. Spacetime itself is an error-correcting code. When information is encoded holographically, errors in the boundary description don't destroy the bulk information. They correspond to local perturbations in the projected spacetime. This means the 3D universe we experience might be the error-corrected reconstruction of data stored on a 2D surface, with the error correction automatically generating the illusion of a third dimension. Evidence number 5, entanglement and geometry. That's when the pattern appeared. In 2013, researchers discovered something that connected quantum mechanics and space-time geometry in an unprecedented way. They showed that quantum entanglement, the spooky connection between particles, is mathematically equivalent to wormholes connecting distant points in space. This is called ER equals EPR. Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs. But here's the truly radical implication. If entanglement creates geometric connections, then the fabric of space itself might emerge from entanglement patterns in the boundary theory. Distance isn't fundamental. Volume isn't fundamental. Three-dimensional space is what quantum entanglement looks like when viewed through the holographic projection. In 2019, researchers proved that in holographic theories, the geometry of spacetime can be completely reconstructed from the pattern of quantum entanglement on the boundary. Cut certain entanglement links and regions of space disconnect. Strengthen certain correlations and space contracts. Space is a hologram generated by quantum information.
Part B. Deeper implications. The cosmological horizon problem. By 2016, physicists began asking, if holography works for black holes and anti-de Sitter space, what about our universe? Our universe isn't anti-de Sitter. It's expanding, with a positive cosmological constant, dark energy pushing galaxies apart. This creates a cosmological horizon, a boundary beyond which light can never reach us because space is expanding faster than light can traverse it. Physicist Tom Banks at Rutgers proposed that this cosmological horizon might be the holographic screen encoding our universe. We think we live in a vast 3D cosmos filled with galaxies and dark matter. We might actually be patterns encoded on a spherical surface receding away from us at light speed. Every atom in your body, every thought in your mind, every star in the sky, all encoded on that distant boundary. But if this is true, it introduces a deeply disturbing question. The projection mechanism. If we're holograms, what's doing the projecting? In a laser hologram, light passes through a 2D interference pattern to create a 3D image. There's a light source and a photographic plate. In the cosmic hologram, what plays those roles? The mathematics suggests that the projection isn't a physical process. It's a duality, two equivalent descriptions of the same reality. The 2D boundary theory and the 3D bulk spacetime aren't cause and effect. They're different languages describing identical physics. Asking which is real is like asking whether a movie is really images on a screen or patterns of voltage in a projector. Both descriptions are complete. But this raises an even more uncomfortable question. If the 2D and 3D descriptions are equivalent and both are complete, then nothing in our 3D experience can distinguish which description is fundamental. There's no experiment you can perform to prove you're not a hologram.
The Planck scale discretization. In 2018, researchers analyzing holographic theories discovered something unexpected. If information is encoded on a 2D surface and there's a maximum information density set by the Planck scale, then the surface must be discrete, divided into Planck-sized pixels. Each pixel can hold approximately 1 bit of information. This means the holographic screen isn't smooth. It's pixelated at a scale of 10 to the negative 35 meters, far smaller than anything we can observe, but fundamentally discrete nonetheless. Our continuous, smooth spacetime is emergent, reconstructed from discrete bits of information. Reality has a resolution. Now, here's what made this discovery profound. If spacetime has a minimum resolution, it means asking what happens at distances smaller than the Planck length is meaningless. There is no smaller. Space doesn't continue infinitely toward the microscopic. It bottoms out at the Planck scale because that's the pixel size of the cosmic hologram. The observer dependence. That's when researchers confronted something that made the entire picture more disturbing. Different observers in an expanding universe have different cosmological horizons. You see a horizon centered on you. I see a horizon centered on me. If holography is observer-dependent, then the 2D screen encoding reality is different for each observer. But we all agree on observations. We share the same reality. This means the holographic encoding must be redundant. Information about the same event must be encoded in multiple overlapping regions of multiple holographic screens. Researchers call this horizon complementarity. The information isn't uniquely located anywhere. It's distributed across all possible holographic boundaries, with the different descriptions remaining consistent through quantum entanglement. This led to a realization that shook physics to its foundation. The evidence no longer pointed to a phenomenon.
It pointed to a flaw in our understanding of reality itself. Act 3. The Big Picture. Part A. Theoretical Framework. The three competing interpretations. Today, three major interpretations attempt to explain what holography actually means, and they paint very different pictures of reality. The emergence interpretation, championed by researchers like Mark van Romstonk at the University of British Columbia, argues that space-time is an emergent phenomenon. The fundamental reality is a quantum system living on the boundary, a system without space or time, just quantum information and correlations. Space-time emerges from this system the way temperature emerges from molecular motion, real and measurable, but not fundamental. This interpretation explains why gravity is so much weaker than other forces. Gravity isn't fundamental, it's a derived property of quantum entanglement patterns. But it struggles with what it means to be an emergent being in an emergent space-time, experiencing an emergent reality. The dimensional reduction interpretation, supported by groups at Princeton and Cambridge, maintains that both descriptions are equally real. The universe is simultaneously 2D and 3D, depending on which mathematical language you choose. Physics doesn't prefer one over the other. This interpretation preserves our intuitive sense of 3D reality while acknowledging the mathematical equivalence with 2D boundary theories. But it offers no physical mechanism for understanding the duality, treating it as a brute mathematical fact. The simulation interpretation, a more radical framework emerging from information-theoretic approaches, proposes that holography reveals something computational about reality. If all the information in a 3D volume is encoded on its 2D boundary, this resembles how computers store 3D simulated worlds in 2D memory arrays. The holographic principle might be evidence that reality is fundamentally computational, that the universe is running on substrate we don't have access to, with the 2D screen being the memory and the 3D experience being the output. Each interpretation explains the mathematics while proposing radically different ontologies. This forces us to reconsider the most basic assumption of all, that there's an objective physical reality independent of mathematical description.
The string theory connection. But beyond these interpretations, holography connects to our deepest theories of fundamental physics. String theory, the attempt to unify gravity and quantum mechanics, naturally produces holographic dualities. The ADS-CFT correspondence emerged from string theory. The mathematics of vibrating strings in higher dimensional spaces maps perfectly onto particle physics in lower dimensional boundaries. This isn't coincidence. Researchers at Stanford and Harvard have shown that string theory may fundamentally be a holographic theory, that all of string theory's extra dimensions might be holographic projections of quantum information living on lower dimensional surfaces. If true, this would mean the fabric of reality emerges from informational patterns with fewer dimensions than we experience. The universe has been running a compression algorithm from the beginning.
The black hole interior problem. This leads to one of the most active research areas in contemporary physics. What's actually inside a black hole? Classical general relativity says there's a smooth interior leading to a singularity, a point of infinite density. But if holography is correct, all information about the interior is encoded on the event horizon. This creates a paradox. The interior can't have more information than the surface encodes, but it seems like it should. Two resolutions have emerged. Fuzzball theory,
proposed by Samir Mathur at Ohio State, suggests black holes don't have interiors at all. The inside is actually a quantum fuzzball at the horizon, with no region of smooth spacetime beyond. What appears from the outside to be empty space inside the horizon is actually maximally dense quantum information at the surface. Part B. Future implications. Testing holography experimentally. In 2023, physicists proposed the first experiments that might detect holographic effects. The idea is subtle. If space-time is emergent from quantum entanglement, then highly entangled quantum systems should exhibit tiny gravitational effects that wouldn't exist if space were fundamental. Researchers at the University of Vienna and MIT are designing ultra-sensitive experiments using quantum optomechanical systems, microscopic mirrors controlled by quantum states of light. If they can create sufficiently strong quantum entanglement between separated systems, the holographic prediction is that a measurable geometric effect should appear, a tiny apparent distance change that emerges purely from entanglement, not from physical motion. The effect would be incredibly small, on the order of 10 to the minus 18 meters. But modern quantum sensors are approaching that sensitivity. Within the next decade, we might have the first experimental evidence that space emerges from quantum information. The quantum gravity connection. Holography is also reshaping how we think about quantum gravity. For decades, physicists have tried to quantize gravity, to make it compatible with quantum mechanics. Every attempt has failed, producing infinities and inconsistencies. But if gravity isn't fundamental, if it emerges from quantum mechanics on a holographic boundary, then we don't need to quantize it. Gravity would be to quantum mechanics what thermodynamics is to statistical mechanics, a useful macroscopic description of deeper microscopic physics. This approach has led to the development of new theories: entanglement entropy gravity, where gravitational equations emerge from the thermodynamics of quantum entanglement; tensor network approaches, where space-time geometry is constructed from quantum circuits connecting boundary information; and causal set theory, where discrete events on the boundary generate continuous space-time through causal relationships. All of these approaches treat holography as a foundational principle rather than a curiosity. The consciousness question. Some researchers have begun exploring an even more radical question. Does holography tell us something about consciousness? The argument goes like this: if the 3D world we experience is a projection from 2D information, our conscious experience is part of that projection. Our brains are patterns in the hologram. Our thoughts are informational processes encoded on the boundary. But subjective experience, what it feels like to be you, seems to be 3D and volumetric. Could consciousness be the projection mechanism? Could the act of experiencing a 3D reality be what generates the holographic reconstruction from boundary information? Philosopher David Chalmers and physicist Max Tegmark have discussed whether the hard problem of consciousness, explaining why there's something it feels like to be conscious, might be related to the holographic projection from information to experience. This is highly speculative, but it raises a disturbing possibility. If consciousness is the projection mechanism, then asking whether you're really 3D or really a 2D hologram is asking whether your subjective experience is real. The answer might be that both are equally real or equally unreal. The multiverse implications. But even if we solve this mystery, it leads to a far more disturbing question. If our universe is a hologram encoded on a cosmic horizon, what about other universes? Eternal inflation theory predicts that our universe is one bubble in an infinite multiverse of bubble universes. Each bubble would have its own cosmological horizon, its own holographic boundary. If holography is universal, then each universe is a different holographic projection from a different boundary configuration. The multiverse wouldn't be a collection of 3D spaces, it would be a collection of 2D information patterns, each projecting a different apparent 3D reality. And here's the truly unsettling implication. If different boundary conditions produce different physics, different forces, different particles, different dimensionality, then the laws of physics themselves are holographically projected. They're not written into the fabric of reality. They're emergent properties of the information pattern. Change the pattern, change the physics.
Act 4. The ultimate questions. When information becomes everything. There's a perspective shift that happens when you truly internalize holography. We typically think of information as something abstract, bits in a computer, words in a book, patterns in a brain. But holography suggests something far more radical. Information isn't a description of reality. Information is reality. The fundamental substrate of existence isn't matter or energy or space-time, it's quantum information, patterns of correlation, entanglement structures, informational relationships. Everything else, particles, forces, space, time, even the dimensionality of reality, emerges from these informational patterns. We're not beings inhabiting a universe, we're informational patterns recognizing ourselves in other informational patterns. This raises a question that philosophers and physicists are only beginning to grapple with. If reality is information, what's it information about? Information requires reference. A map implies a territory. But if the territory is itself informational, what grounds the reference? One answer is that reality is self-referential information. The cosmic hologram encodes information about itself, creating a strange loop where existence is simultaneously the message and the medium.
The measurement problem connection. This connects to quantum mechanics in an unexpected way. The measurement problem, why quantum superpositions collapse to definite outcomes when observed, has puzzled physicists for a century. But in a holographic universe, measurement takes on new meaning. When you observe a quantum system, you're entangling your information state with the system's information state. The collapse is the holographic projection selecting a consistent 3D narrative from the 2D information. The reason measurement seems to create reality is because it literally does. Before measurement, the information exists in superposition on the boundary. The 3D projection contains multiple overlapping possibilities. Measurement forces the selection of a single consistent projection. Reality isn't discovered by measurement, it's constructed by measurement from the informational substrate. This means that observers, information processing systems capable of entanglement, are fundamental to the holographic projection. Without observers, the universe remains encoded on the boundary, never projecting into definite 3D form. Consciousness isn't separate from physics. It's the mechanism of holographic projection.
The computational universe. Several physicists have pushed this even further. If reality is information, and information is computational, then the universe might literally be a computer. Not metaphorically, literally.
Researchers like Seth Lloyd at MIT have calculated that the universe, treated as a quantum computer, has performed approximately 10 to the 120 operations since the Big Bang, processing information at the Planck scale. Every particle interaction is a computational step. Every quantum measurement is a bit operation. The universe is computing itself into existence. But here's the disturbing question: what algorithm is it running? The laws of physics might not be constraints on how matter behaves. They might be the code, the program running on the cosmic quantum computer. And if the universe is computational, then the holographic boundary isn't just encoding information. It's the memory storage for the universal computation. The 2D surface is the hard drive. The 3D reality is what's displayed on the screen. You're not just living in a simulation. You are the simulation. The ultimate nature of reality. This forces us to confront the deepest question in all of philosophy. What does it mean for something to be real? We've discovered that space emerges from quantum entanglement. Time might emerge from increasing entanglement entropy. Particles are excitations in quantum fields. Fields are projections from holographic boundaries. Boundaries encode information. Information is processed computationally. At every level, what seems fundamental turns out to be emergent. Reality is layers of emergence built on layers of emergence, with each layer equally real in the sense that it obeys precise mathematical laws and produces consistent observations. But is there a bottom layer? Is there some ultimately fundamental substrate, or is it emergence all the way down? Physicist John Wheeler proposed it decades ago. It from bit. All physical existence emerges from information, from yes or no questions, from binary distinctions, from the simplest possible building blocks of knowledge. The universe is made of questions, and we are the universe asking itself those questions.
The question we cannot answer. And that brings us to the question this entire journey has been circling. We've discussed how holography resolves paradoxes, what it means for space-time to be emergent, how information might be the fundamental substrate of reality. But we haven't answered the deepest question of all. If we're holograms, if our entire experience is a projection from information encoded on a distant boundary, why does it feel like anything at all? Why is there subjective experience? Why does the projection include consciousness? A hologram made of light and interference patterns doesn't feel like anything. It just exists as a physical structure. But you don't just exist as a pattern of information. You experience being that pattern. There's something it's like to be you. Holography explains the structure of reality. It doesn't explain why reality is experienced. And that might be the ultimate mystery. Not how the projection works, but why there's anyone to witness it. Two possibilities emerge, neither comforting. First, consciousness is fundamental, woven into the informational substrate at the deepest level. The universe doesn't just process information, it experiences processing information. You're not an emergent phenomenon in an unconscious universe. You're how the universe experiences itself locally. Second, consciousness is the ultimate emergence, appearing only in sufficiently complex informational patterns. It's real, but it's the highest level layer of the holographic projection. Both answers suggest that solving the physics of reality doesn't solve the mystery of experience. The hologram can be completely understood mathematically, and yet the fact that there's something it feels like to be part of it remains unexplained. The question we cannot answer. And that brings us to the question this entire journey has been circling. We've discussed how holography resolves paradoxes, what it means for space-time to be emergent, how information might be the fundamental substrate of reality. But we haven't answered the deepest question of all. If we're holograms, if our entire experience is a projection from information encoded on a distant boundary, why does it feel like anything at all? Why is there subjective experience? Why does the projection include consciousness? A hologram made of light and interference patterns doesn't feel like anything. It just exists as a physical structure. But you don't just exist as a pattern of information. You experience being that pattern. There's something it's like to be you. Holography explains the structure of reality. It doesn't explain why reality is experienced. And that might be the ultimate mystery. Not how the projection works, but why there's anyone to witness it. Two possibilities emerge, neither comforting. First, consciousness is fundamental, woven into the informational substrate at the deepest level. The universe doesn't just process information, it experiences processing information. You're not an emergent phenomenon in an unconscious universe. You're how the universe experiences itself locally. Second, consciousness is the ultimate emergence, appearing only in sufficiently complex informational patterns. It's real, but it's the highest level layer of the holographic projection. Both answers suggest that solving the physics of reality doesn't solve the mystery of experience. The hologram can be completely understood mathematically, and yet the fact that there's something it feels like to be part of it remains unexplained.
And somewhere, right now, a researcher is scribbling equations that might reveal the next layer of emergence, the deeper principle from which even holography itself emerges. When that discovery comes, our picture of reality will shift again. Because that's what physics does. It doesn't reveal ultimate truth. It peels back layers, finding deeper patterns, more fundamental principles, stranger symmetries. The universe does not owe us simplicity. It does not bend its structure to match our intuitions about what's real. Holography is not an anomaly. It's an invitation to question every assumption, to venture beyond the comfortable illusion of 3D permanence, to explore the informational substrate underlying existence. You are a hologram contemplating the nature of holograms. You are information wondering what information is. You are the universe asking itself what it means to be. We are still learning how strange reality truly is. The journey has only just begun.